Namaste. Welcome to the lecture series on the subject Basic Thermodynamics, Module 5, Part 1, Ideal Gases. Lecture number 3. Myself, Dr. Nsatheeshkumar, Associate Professor of Mechanical Engineering, Canara Engineering College. The contents for this topic are gas constant for the mixture, molecular weight of the mixture, entropy of the mixture, isentropic process of gaseous mixture. Now let us derive the expression for the gas constant for the mixture. So let us assume there are two constant gases A and B. Now if you write the characteristic gas equation for constant A, so then it is PAV into MARA into T. So you can see there is no suffix for volume and temperature, because here it is assumed that even the constant gases occupy the same volume of the mixture at the temperature of the mixture. Similarly, you can write for the constant gas B, PB into V is equal to MBRB into T, and if you add these two expressions, you will get PA plus PB into V is equal to MARA plus MBRB into T. Now the mixture is also behaves like a perfect gas, so for the mixture you can write PV is equal to MRT. Now you know the Dalton's law of partial pressure, which states that the pressure of the mixture of gas is equal to the sum of the partial pressures of the individual components, if each component is considered to exist alone at the temperature and volume of the mixture. So that is why there is no suffix is taken for temperature and volume. You can see here the first two expressions, there is no suffix taken for the for the constant gases also. So it is also assumed to exist at the mixture volume and at the mixture temperature. So you can write from the Dalton's law of partial pressures, P is equal to PA plus PB. So if you multiply by V on both sides, so here you will get PV. So here PA plus PB into V. So that is from here, expression here, I use a different color. This is from here. PA plus PB into V is nothing but MA plus RA, MARA plus MBRB into T. Now from equations 1 and 2, you can write MR is equal to MARA plus MBRB. Now R is equal to MARA plus MBRB by M. So this is the expression for the gas constant of the mixture. So here M is the mass of the constant gas A, RA is the gas constant for A. Similarly, MB is the mass and RB is the gas constant for the constant gas B. M is the total mass of the mixture. Okay. Also, for the gas mixture, you know that PAV is equal to MARA into T, but MA, that the mass of the gas, is also equal to the molecular weight into number of molecules. So that also we studied in one of the earlier lectures. So you can write PA into V is equal to NA capital MARA into T. Now here the product of molecular weight and characteristic gas constant MA into RA, so you can write it as R bar, because that is a constant for all gases. So the product of molecular weight and gas constant is universal gas constant, and its value is same for all the gases. So you can write PA into V is equal to NA into R bar into T. Similarly, you can write PV is equal to N into R bar T for the mixture, and if you divide, you can write PA by P is equal to NA by N into is equal to YA. That is nothing but the mole fraction. See, this is the mole fraction of A, because N is the number of moles of A and this is the total number of moles. Here it is the partial pressure of A and this is the total pressure of the mixture. So this partial pressure divided by total pressure is equal to number of moles of A divided by total number of moles is equal to mole fraction of constant gas A. Similarly, you can write mole fraction is also equal to the volume fraction. That means Ya, that is mole fraction, is equal to Pa by P from the previous slide, is also equal to Na by N. So this you can also write as Va by V, that is equal to volume fraction. Now let us find out the molecular weight of the mixture, I mean the expression for the molecular weight of the mixture. So once again we can write PaV is equal to MaReAt, and also you can write in place of mass of A, you can write as Na into Ma. Similarly you can write for constant gas B, Pb into V is equal to Nb Mb Rb into T. So Pa plus Pb into V is equal to Na MaRa plus Nb Mb Rb into T. So this is by adding the gas equations for the individual constant gases. So here we have considered only two gases. Also PV is equal to NMRT for the mixture, and by Dalton's law of partial pressures, P is equal to Pa plus Pb. So you can write NMRT is equal to Na MaRa plus Nb Mb Rb into T. So similar to the previous derivation. Okay. So you can write, you see all this T gets cancelled on either side. Mr, now Mr is here, okay, is equal to, now what we did is this N is taken to the other side. So it becomes Na by N, and when it comes to here it becomes Nb by N. So Na by N is nothing but Ya, that is nothing but the mole fraction. Similarly Nb by N is nothing but Yb, mole fraction of B. So you will get the expression Mr is equal to Ya into MaRa plus Yb into Mb Rb. So you want the expression for the molecular weight, so you can write Ya into MaRa plus Yb into Mb Rb divided by R. So this is one of the expressions for the molecular weight of the mixture. If you know the mole fraction of each of the constant gases, molecular weight of each of the constant gases, and the gas constant for that gas, you can find out the molecular weight of the mixture. We also know that Mr is equal to MaRa plus Mb Rb. This is from the first derivation. So you can write R is equal to MFA into Ra plus MFB into Rb. So how did you get MFA? That is nothing but mass of A here divided by this M when it comes to this side. So MFA is nothing but Ma by Ra. Similarly Mb by M is equal to MFB. So you will get MFA and MFB here. And also you know that this gas constant R is equal to R bar by M. And if you write it for A, constant gas A, it is Ra is equal to R bar by Ma, and for B it is Rb is equal to R bar by Mb. Now if you substitute this R, Ra and Rb in this expression, you will get R bar by M is equal to MFA as it is, in place of Ra as R bar by Ma plus MFB as it is, and in place of Rb, R bar by Mb. So R bar gets cancelled here from all the three terms on either side. Okay. So 1 by M is equal to MFA by Ma plus MFB by Mb. If you simplify this, you will get MFA into Mb plus MFB into Ma divided by Ma Mb. And if you take the reciprocal of that equation, you will get expression for molecular weight of the mixture as molecular weight of A into molecular weight of B divided by mass fraction of A into molecular weight of B plus mass fraction of B into molecular weight of A. Now let us come to the entropy of the gas mixture. So you know that entropy of a gas mixture, Sm, is nothing but entropy of the individual constant gases, that is Sa plus Sb plus Sc. The specific entropy on the mass basis, now suppose this is the total entropy. Now if you write on mass basis, so Sm is equal to mass fraction of A into Sc, mass fraction of B into Sb plus mass fraction of C into Sc. So here this is total, So you have to write mass into specific for each of these individual constant gases. But here this doesn't change because this is the total entropy of the mixture, right? That is also for specific mass, specific quantity, because here it is you have taken mass fraction. So this also becomes for the this becomes specific entropy only. Now on differentiating, so you will get dsm is equal to mfe into dsc plus mfb into dsb plus mfc into dsc and so on. So expressing the entropy of a perfect gas as a function of temperature and pressure, the change in entropy is given by, okay, this is the expression for change in entropy when it is expressed as a function of temperature and pressure, that is a ds is equal to cp into dt by t minus r into dp by p. On substituting this expression in the above equation, the change in entropy of a gas mixture in the differential form becomes dsm is equal to mfa into entropy of A. Now you have to write Cp of A into dt by t minus Ra into dpa by pa plus mfb and this expression for B, mfc and expression for C. Assuming the specific heats as constant and integrating the above equation between states 1 and 2, the change in entropy of a perfect gas mixture on the mass basis can be written as, look at here, S2 minus S1 for the mixture, MFA. Now CPA, if it is constant, so integration of 1 by t with respect to t here is nothing but ln t. If you apply the limits, it becomes ln t2 by t1. Similarly, integration of 1 by PA with respect to PA is nothing but ln PA. If you apply the limit, it becomes ln PA2 by ln PA1. Similarly, you can do it for the rest of the two gases also, and you will get this expression for the change in entropy of the perfect gas mixture. Similarly, the change in entropy in the gas mixture on molal basis, that is number of mole basis, you can write it as S2 bar minus S1 bar for the mixture is equal to Ya, mole fraction of A, into C bar P, A for A into ln T2 by T1 minus R bar A ln Pa2 by Pa1. This is for constant gas A. Similarly, you can write it for B and C, and all are added to get the entropy change of the mixture on molal basis. Here Pa1, Pb1, Pc1 etc. are the partial pressures of at state 1, and Pa2, Pb2 and Pc2 are the partial pressures at state 2 of the constant gas ABC respectively. Now coming to the isentropic process of gas mixture. When the mixture of gases is compressed or expanded from state 1 to 2 isentropically, that means for isentropic process 1 to 2, maybe the process is compression or expansion, you can write T2 by T1 is equal to P2 by P1 to the power gamma mixture minus 1 divided by gamma mixture. So general formula is T2 by T1 is equal to P2 by P1 to the power n minus 1 by n, but for a isentropic process n becomes equal to gamma, but here it is gamma is for the mixture, so you have to write gamma m. You can see here you have to write gamma for the mixture, where gamma m is the specific heat ratio of the gaseous mixture, which is given by the specific heat at constant pressure for the mixture divided by the specific heat at constant volume for the mixture. So now the specific heat at a constant pressure is nothing but MFA into Cp of A plus MFB into Cp of B, whereas specific heat at constant volume for the mixture is nothing but MFA into Cv for A plus MFB into Cv for B. So you can write MA into Cpa plus MB into Cpb divided by MA into Cva plus MB into Cvb, because MFA is nothing but MA by M. Similarly, MFB is nothing but MB by M. So you can write MFA and MFB as mass of A and mass of B also you can write. And on molal basis, so you can write the specific ratio of the specific heats for the mixture gamma m bar as this expression, Cp bar for mixture divided by Cv bar mixture. So Cp and Cv all should be taken for the on molar basis. Okay. With this I conclude this lecture number 3 and will continue with lecture number 4 in the next lecture. Okay. Thank you.